great pleasure to have Maggesi talking to us about building proofs and countermodels in light of the probability logic GL. Thank you.
Thank you. Thank you to all of us, all of you for coming, and hi. And thank you to the organizers for inviting me and for all the work. Which, Okay, so during Thursdays I speak with some of you, and it seems to me that nobody is familiar with modal logic and probability logic. So I'll try to give an introduction. So sorry for the people who are already familiar with the subject if this will be boring for you, and I hope it is useful for the other people. This is a joint work with my collaborator Cosimo Perini Brogi for IMT Lucca. So let's start. Let me try to give a very quick intuition of what modal logic is, just to have an idea. And so let's start with the syntax. So we have propositional, the formulas in modal logic are formulas of propositional logic. So with the classical quantifier, classical connectives like negation, implication, disjunction, and conjunction, and two new operators called modal operators, which are box and diamond. So for any formula P, you can consider box P and diamond P.
Marco, some of us do intuitionistic modal logic. Okay, just saying.
I
do.
Yes. I'm in a classical setting. In my
makes sense. Introduction.
Okay. So the first thing that is useful to know is that box and diamond are dual each other. So this means that if you do the negation of box P, this is the same as a diamond of negation of P, and the same for diamond and box. And this is very much like, sorry, I don't understand why sometimes doesn't work, this. Okay. There is a strong analogy with the quantifiers for all and exists. And this means in particular that you can define diamond in terms of box, and you can define box in terms of diamond. And very often we take just one of the two operators as the primitive, and the other is just an abbreviation of the other, of the dual. Okay. Sorry. Okay, so we don't have one modal logic, but we have a family of modal logics of systems, and in each system the operators box and diamond can be interpreted in various ways. So we can have, for instance, analytic interpretation where box means necessary, so box P means P is necessary, and diamond means possible. Or we have, let me try with this one, epistemic logic, where box means we know that, and we don't have a name for the dual, but it's not important. And or we have another interpretation is epistemic with respect to belief, so box means beliefs. Or deontic logic, where it means obligatory, box means obligatory, and diamond means permissible. Or temporal logic, where box means always and diamond means eventually. And the thing that we are interested mostly today is the probability logic, where box means it is probable that. And there are relations between the various systems. So in this diagram, there are 8 systems pictured, which are the vertex of the cube. And the arrows means that one system is the extension of the another. So the minimal system in some sense is K. It's called K for Greek key, which made the semantics for modal logic and many other things in modal logic. And you can interpret the side of the cube, for instance, as adding an axiom. So you start with a minimal system. If you add an axiom, you go in one direction. You obtain, for instance, system D. If you add another axiom, you obtain another system, and you get this picture.
Marco, can we go back to modalities, to the previous slide? I have a question. For the case of interest today, provability.
Yes.
You have blank for diamond, but could you have an interpretation of diamond as is consistent? Because it's not the case that the negation is...
Well, it is consistent. Yes, I will show that later.
Okay.
The interpretation as is consistent, at least for me, is clear in one particular case when P is truth. When for a special case of formula. Okay. For now, it is just easy to say that diamond is. It is false that we can prove that P is false. The negation of P. Okay. No, doesn't work. Okay.
So is it like not even wrong in the physics sense?
Sorry?
It's like not even wrong in the famous critique of string theory.
So, yes, a little bit, yes. And but there are many other modal systems. Here there is a picture with some more systems. So the picture gets more and more complicated if you want to consider a larger set of examples. This picture, for instance, is taken from a paper from Benzmüller et al., which is about an interpretation, a verification of the relation between all these logics, all these modal systems in Isabelle HOL. This is just to give you an idea, and there are even more systems. For instance, if you take one side of the cube, which is the side K4, you can picture many other systems here, and the system that we are interested in is here in this side. So if you want, you can consider many examples of modal systems. Please. What are these arrows? Arrows means that one system is an extension of the other. For instance, that one system you start from the minimal system K, you add axioms, and you obtain another system which has more theorems which are provable because it is extended. Okay?
But isn't the case that arrows now look in opposite direction?
Yes, the two pictures are not coherent, sorry, because they are taken from different sources. Sorry. But what you have to keep in mind is the K is the minimal system and the other are extensions, okay? And this is just to have an idea of the variety of modal systems that you can have, and correspondingly the variety of interpretations that you can have for the box and diamond operators. Okay, so when you study a logical system, you have two main techniques and tools, which are semantics and calculus. So for the semantics, there is an approach which is called the possible words semantics, which is due to Kripke, and we call them frames. Frames are structures which are done by a set of words. Here there is a picture where I have some dots which represents possible words. So, for instance, we have here a word which we call W1, W2, W3, W4, etc. And then we have what we call the accessibility relation, which makes words in relation between them. And we can think our semantics has the fact that we are traveling in this diagram, we are walking in this diagram, going from one word to another word. For instance, because there is an evolution or because time passes or things like that. And the box, so for every formula of our logic, we can have the formula valid in one word but not in another word. So let's say you have a formula P. P can be false on W1, true on W3, and false on W4, etc. And the interpretation of the box and diamond operators means that the formula will be, for the box operator means the formula will be always true if you walk in the diagram after a while. And the diamond operator means that your formula will eventually become true if you walk in your diagram. To make a more concrete example, let's consider a simpler example for temporal modal logic. So the set of words is given by instant of time. So you have, for instance, dots. Let's consider a discrete time for simplicity. You have the dots here represent time, and so you have T0, T1, T2, T3, etc. And the accessibility relation is the fact that you can go from one instant to the next one. And so, for instance, a formula P means that the property is true for all time. It's always true for all t. Box P means that the property PT it becomes true after a given, there exists an instant capital T, after a while PT becomes true, and the box P means that for all capital T there exists a time T bigger than T, the capital T, that where P is true, okay? So in this case, P is true independent from the instant, and box P it will become always true, and diamond P means it will be eventually true, okay? So for instance, an example of P can be 2 plus 2 is equal to 4, does not depend on time. And an example of diamond P will be it rain. Perhaps it does not rain today, but eventually it will rain, we hope. Okay?
Sorry, Matt.
Yes?
Just a shallow question. the implication and conjunction on the right are meta levels, are meta symbols, or are part
Yes.
of the logic?
Yes. So in the column here, we have the formula in modal logic, and here we have their interpretation.
Okay.
In the meta language.
Thanks.
Yeah.
Sorry. And here your key frames are not necessarily satisfying a persistence property or anything like that. Or
A persistence.
persistence property for accessibility in that if a world can be accessed from another and this world believes in something, then all the worlds that are from it also believe in that thing. You're not necessarily assuming this.
In this example, it's not necessary. There are many examples of frames and properties that you want to require according to the system that you want to study.
Okay.
Yeah. Okay. So now let's go to the special case of modal system that we are interested today. So logic of probability. The origin of the system is that, as we know, there are theories that are able to investigate their own notion of probability, so what we call self-reference, like Peano arithmetics and the process of Gödel of looking for probability inside Peano arithmetics. So the intuition in this case of the box operator is that box P means what usually it's notated like this, that you take the proposition P, you take the Gödel number associated to P, and you make the proposition that says that this Gödel number is the Gödel number of a proposition which is provable. Okay? And so, in short, this means P is provable. But it is expressed inside Peano arithmetics. Okay? And a diamond P, so it is not box not P, it is not provable that P is false. This is the easiest interpretation. So, for instance, you have very surprising results like Leb theorem. So Leb theorem says the following. For any proposition P of Peano arithmetics, sorry I didn't wrote here, if Peano arithmetics can prove that the probability of P implies P, then Peano arithmetic can prove P. This is a surprising result. So, to prove P, it is enough to prove that from the probability of P, you can deduce P. It's not, for me, it's hard to understand. So, it's hard to have an intuition why this is true. And so this is the kind of result we obtain in arithmetic. And so if you want to express this in the modal logic GL, this become, you can write it in just one theory, axiom, yes. This is written as a deduction, but here you can write it as an axiom, which is box of box P implies P implies box P. Okay?
And that one makes lots more sense, right? Because you think of it and say, if P is provable, then P is true. And if this whole thing is provable, then it's provable that P.
Yeah. Yeah. And just to understand why this is a nice result, we can see Loeb theorem has a kind of undecidability result. So, Loeb theorem can be seen as a very elegant incompleteness result. And to see it, just take P equal false. So the idea is you start with lob theorem, okay? Or axiom, so theorem in piano arithmetic or axiom in GL logic, okay? You replace P with bottom, with false. Then you use consistency. Consistency can be written like this. Box P implies not box not P. Why? Because if you can prove P, and your system is consistent, you cannot prove that P is false, right? And so if you use this with this one, okay, with box bottom, you obtain exactly, you obtain precisely not box, not false. But not false is true, and true is provable. So this becomes false. And if you use the definition of negation, this becomes not box false, okay? So it means you cannot prove that, you cannot prove false, which is an undecidable result of incompleteness. And so this is a very powerful tool, and for instance, the second incompleteness theorem of Gödel can be derived from this one very easily.
But you have to admit that kind of putting a box in front of false looks very odd by itself.
Yeah.
Right? Because it says false is provable. Odd.
Yeah. So, just to make a little bit more practice with this formalism, let's see how you can write formally in the GL logic the second incompleteness theorem of Gödel. So you start by another way of saying that the system is consistent, which is not box false. So you cannot prove false. Or if you want diamond T, which is what was I think it was thinking James before. And so you cannot prove consistency means not box false, or not box diamond true. And the second incompleteness theorem is not box not implies not box true, or in a more compact form, diamond true implies not box diamond true. Okay? This is just to have an idea of what you can do with this kind of logic. Okay? Okay. So if you are just lost, don't worry. It's not very important to have all these details in mind.
I mean, that's maybe, I mean, that's one of the, I mean, one way to understand the, I mean, just to have your opinion on this. If you go back to the Gödel, not before, the formula itself.
The previous one?
Yeah, before, yeah, before. The one before.
Encore,
So would you agree to say that what the theorem says is that the formal system doesn't have access to what has been established externally about the probability? I mean, you know, one way to understand.
So I must say that I don't understand this. It is something that I find difficult to understand from an intuitive point of view.
Yes. The question is, I think there's a mechanical way, yes, to extract. So,
A mechanical way to extract what?
I mean, so imagine that you have a proof, because it says that, if you want to, you cannot use the probability of P to prove P, yes, because you don't have access inside the formal system. You cannot simply, maybe I could say, linearize the proof, or decode the proof. Yes? But the theory, I think there's a mechanical, it's a question here, a mechanical way to extract from the proof here, above.
From you mean from this?
Yes.
Yes, this is mechanical. In principle, this is mechanical.
It's recursive, I think. Yes.
Yes.
Sorry.
Please.
I guess if this helps people, this is equivalent to having K4 plus multiple fixed points. And so you can think of this as some kind of like fixed point, kind of similar to a fixed point kind of thing.
But you will show that later, right?
Yeah.
You can imagine, yes.
Yeah.
You will speak about well-founded models.
Yeah. Well, I'm not a specialist of this, so I'm not sure if it is the case or not. But
You can derive this one from K4 plus a multiple fixed point thing. And I believe this also implies K4 multiple fixed points as well. So you can think of this as almost like a fixed point thing, and there's a connection to the Y combinator.
yeah. Okay, so.
Sorry for interrupting you.
Oh, no, it's okay. Please. So, what is important at this point is that modal logic is cool. The GL is nice, and you can do very nice. You can use it to model reasoning about self-reference. And now, what is important is that. GL is sounded complete with respect to a suitable class of frames. So we have a Kripke semantics for GL, which is given by irreflexive, transitive, finite frames. So something not too complicated. And for people who know how, know the subject, this is more. This gives, in an obvious way a way to decide to prove that the GL is decidable, and so it would be nice to have an automatic theorem prover for GL. That is a machine that, given a statement P that it's true, it proves P. Given a statement P which is not true, it gives a reason why it's not true. So it gives a counter model in the Kripke semantics, and it is mechanically verified. So it's not a program written in a language where the correctness is an extra meta reasoning, but it is formalized in a theorem prover. And this is what we did, and which I'm going to discuss now in this seminar, in the rest of this seminar. So, a new overview of our work is we developed in the HOL light theorem prover a deep embedding of the modal logic GL, a computer check proof of meta-theoretical properties of GL, including correctness and completeness with respect to the ETF semantics, and an implementation of a decision procedure for GL. And I like very much this diagram due to Barengret, the so-called Barengret's triangle, where he tried to synthesize the main important activities in mathematics, which are defining, calculating, and reasoning, which interacts each other. And so in this view, we have that the deep embedding is the defining, it's mostly the defining activity. The meta theory is the reasoning, and the implementation of decision procedure is something about calculating. And one of the difficulty that you have in this kind of activity is that you have a stratification of languages. So you start with GL. GL, for instance, here you have this is the formulation of, just to give an example, the formulation of the second incompleteness theorem of Gödel. And I use green in this slide to denote, for formulas of GL. And you have a larger container which is high order logic. And for instance, here you have the necessitation rule is one of the rules of the logic. And you see I use green for the GL formulas and theorems, and blue for the HOL syntax. So here you have a theorem of HOL that says that for any formula A, you have this implication, okay? And of course, you have another language, which is the meta language, or CAML, which is the language used in HOL light. And so you have, now I use black, for the code that you have to write in HOL light, okay? So you have, for instance, a rule for proving theorem of GL, and this is the end of the instruction. The quotes says that what you have inside is a term, and inside you have the term of HOL logic, of the whole logic, and the green part is the GL logic, okay? So why do all this? Because for many reasons, of course, this is a part of an effort to studying the bending of logics in theorem provers, and to study meta logic, and to do transformation and symbolic manipulation in automatic but certified way, and all that. And this is a long-term goal. And more concrete goal for the near future are generalize our work to other modal logic, say normal modal logic. And another thing which should be reachable is formalize an interesting theorem, which is the arithmetic completeness, which in particular justify the use of the GL logic to deduce things for piano arithmetics. I'm not going, we started a work for generalize our framework to normal modal logics, but I'm not going to speak about this today. So we have the work is divided in 4 parts. So there is the syntax and semantics for modal logic in HOL, and this has been done in the Harrison's tutorial. So it is something that you can find as an exercise to learn HOL. The second part is starting doing specifically reasoning about GL, and so write the axiomatic calculus of GL and the soundness theorem, and then prove the completeness of GL with respect to the ITF semantics. And this is quite a lot of work. And this is what we did in a conference paper in 2020. And later we use the completeness of GL to implement a decision procedure for GL. This has been published last year, and now we are working on the generalization to normal modal logics. And we hope to finish this year, but I don't know if it will be possible. So let me say very few things about HOL light, just to make readable the slides that the next slides. So we have, let's just me say something about the notation of HOL. So we have the informal notation here that you know very well. And the HOL notation use keyboard symbols. So you have F for false, true, tilde for negation, and graphical symbols for the binary connectives. This is the notation for a theorem. The quantifiers are exclamation point, interrogation mark, and this is the lambda notation, and this is the membership notation. And we need another, we need special notations also for the GL formulas. So we have a false, true, not P, and these symbols which are specific for the internal logic that we are considering. Then we have the box operator, and we have a symbol which is similar to the turnstile of HOL, but which is with a double dash to denote the probability inside the GL system. Okay? So for instance, we have, here there is an example with external and internal conjunction. So this is a theorem of HOL that for all P and Q propositions, if you can prove in GL P and Q, you can prove in GL P and Q if and only if you can prove in GL P and you can prove in GL Q. Okay? Again, the green formula is in GL, are in GL, and the blue formulas are, and the rest of the formula is blue because it is in HOL.
Should I consider this as the axiomatization of the conjunction in GL?
Yes, so there is an axiomatization which involves essentially implication, negation, and box, and conjunction is defined with implication and negation.
So this is not the definition, right?
This is not an axiom. This is not an axiom. It's just an example of formula. So for instance, this is modus ponens. Modus ponens is a theorem of the higher order logic that says that for all P and Q, if you can prove in GL P implies Q, and you can prove in GL P, then you can prove Q. Okay? Another example is necessitation rule, which is one of the rules of the normal modal logics. So for all P, if you can prove P, you can prove box P. Well, and this is another, in our notation, the second incompleteness theorem. Okay. So, how much time I have? 20 minutes?
That's right. I mean, but that means no questions. But we have some.
Okay. Please.
What do we do with the lambda abstraction in the language? Included that in the.
It's not included in GL.
All right. Then you don't need that.
I need at the meta level For instance, for transforming formulas of GL, but it's not part of the GL fragment.
Then you need also application and data construction in the meta logic or in the
meta logic, yeah. Yes, because I need to manipulate formulas and reasoning. I need to reason about formulas and all that. Okay, so I don't have so much time to do all what I want to do. So let me say quickly something. So first of all, we give a data type of formulas that we call form, and the data type of formulas has the usual constructions, the construction that you can expect. So there is truth, atoms, negation, conjunction, disjunction, implication, by implication, and box. The diamond, it's not given in the syntax because you can obtain it by duality. Then we define the semantics of, in HOL, the semantics of possible words. So the idea is that you take a type, the notation double with the colon means that this is a type. You take a type and you take a predicate over this type. So here this W and this W are not the same W because one is a type and the other is a predicate. And in HOL there is no problem because the namespaces are not the same. Okay. And then you need an accessibility relation, the edges of the graph that we saw. So this is a binary relation R on W. And we define a predicate which takes a relation which holds, which takes a frame, so a pair WR, an evaluation function, so a truth assignment function, a formula P, and a word W. So V is the truth assignment function, which is a function that takes a string, which is the name of the atom, an element W of the type of words, and gives you a boolean, which says if the atom is true or false. And from this, you can abstract over the words, and so you can define a new relation which is holds in, which take the frame and the proposition, and by definition it is if for all VW, W in the is a if W is a word, holds with the frame, the evaluation, the proposition, and the word. And finally, we abstract over the frames. So we have a set of frames L, which is our interpretation of the logic, and so P is valid on the set of frames L if and only if for all frame F, LF implies holds in FP. And this is the semantics, the Kripke semantics for modal logic in general. Now, for GL, we consider the irreflexive transitive frames. So it means that we have a pair WR where, well, W is not empty, otherwise it's not a frame. And R is well defined, so RXY means that X and Y are words. W is finite. R is irreflexive, so for all X in W, not RXX, and it is transitive. And there is another interesting set of frames which are the transitive transitive Noetherian frames. which is useful to consider because they are the frames, they are precisely the frames where the lob axiom is valid. I'm not going to speak about that, it's not important.
You use some predicate there, sorry, well-founded? If you define it by...
Yes. Well, this means well-founded, yes.
And it's from the specification or it's from...
No, it's already in the system. There is a huge library about binary relation and all that in HOL Light. So we use something that was already defined. Okay, let me skip something. Okay, so this is for the semantic part, and now we have the axiomatic part. From the axiomatic point of view, we have the usual axiomatization of a classical propositional logic. We use the one that we found in the book of Mendelssohn, plus some specific axiom schemas for modal logic. So the first one is the schema K, which is valid in K and in all normal modal logics, which is a kind of distributivity of box over implication. So box A implies B, implies box A, implies box B. Okay, and this gives you this with the necessitation rules, which says that if you can prove A, you can prove box A, gives the modal logic K. And to have the logic GL, you have to add another axiom, which is the lob axiom schema, which we saw, which is the axiom corresponding to lob theorem. So soundness is very easy to prove. The soundness theorem is that for all proposition P, if you can prove P, then you can prove that P is valid in the ITF semantics. And this is an easy result. Then you want to prove completeness, and before doing that, you have to prove a lot of things axiomatically in the GL logic. So, for instance, this is a simple theorem that you want to prove, which is the box P implies box P. So you can prove this using all these previously given results. For instance, this is P and Q implies P, and there are several basic results that you can use. And from these results, by first order reasoning, you can prove this. And our strategy in this case is to use HOL Light automatization to obtain the theorem. It works quite well for simple cases. And this is something that you can do, an example of something that you are able to do. So prove this result from these results. There is several tools in HOL Light for doing automatic theorem proving, like Metis and Mason and things like that. And it is enough in several cases. But there are other results which are not easily provable automatically. For instance, one example is this one, which is the substitution in biconditional. So if you have, this is a rule, if you have that P if and only if P prime and Q if and only if Q prime, you can prove P if and only if Q, if and only if P prime, if and only if Q prime. So for this one we had to do an interactive proof, which was quite heavy actually, and quite boring. And we had to do this for several lemmas reasoning inside the GL axiomatic system.
Why is it complicated if you have the transitivity in the rules in the previous one? In the previous slide, you have the transitivity of implication.
Which transitivity?
If you rule in the first row, this rule, you have this one. Then
I don't remember why. Let me think. I don't know.
Okay, now we can postpone that.
Perhaps because this has been proved after the other one. So even if the slides speak about this theorem before, but the other one has been done before. Yeah, I think so. I have to check, but probably this is the reason. So in total, we had to prove 150 such lemmas. And this is necessary to bootstrap our system to prove the consistency of, to prove the consistency of the GL logic. And it was quite heavy and quite a lot of work to do that. And it can be interesting to experiment with this to see if there are better ways to obtain the same result in an automatic way. So, with this we can prove the completeness theorem. The completeness theorem is the hard part from the mathematical point of view of our work, which says that if you have a proposition, it's the other direction in some sense. So if you have a proposition, if you have a formula P, if P is valid, then P is provable. Now, it is a little bit late. There are some technical details about this proof. This proof has been, we found the proof in, there is a beautiful book of Boulos, which gives the completeness theorem for several modal logics and gives the essential ideas. There are some technical points. It turns out that the proof given in Boulos is very good, but it's not very easy to write in a formal system. So we had to do some modification to make the proof easy to implement formally. But I'm not going to speak about that. It's a little bit technical, it's too late. So let me skip some details. And using completeness, we can provide a decision procedure. So, for instance, there are several ways you can give a decision procedure for a model logic like GEL. So one way is to reason inside the axiomatic calculus, but this is notoriously difficult. So you can use first order automatization like Mason and Metis. And this is what we do for many of the 150 lemmas that I mentioned before, but it's quite complicated. It does not work very well in general. So this is not something that is not doable in general. Another approach is to use completeness, so reduce the proof of the probability of a proposition into the semantic version, then expand in the Kripke semantics, and again use first order automatization. And this works better. There are several things that can be proved in this way. But again, the most complicated examples does not work. So this is not something that we want to use. And also this is something very heuristic. So can work or can be unreachable because the size of the problem is too big. And the best approach is something that is known in the literature, is using an ad hoc proof search which is guided by structural proof theories. There is a work by Sara Negri from 2014 that explain how to, that gives a calculus for GL that can be used for this. So what we did is using this calculus for, let me skip so some details about the system, the rules of the system. By we implemented a shallow embedding of the calculus of Sara Negri in the crypt key semantics of GL. And what we obtain is a proof search which is directed, that has no guesses, you have no branching. And when it fails, it gives, so when it does not reach the end of the proof, it cannot construct the full derivation, it gives you a counter model of your formula. And so our procedure is take a goal in the GL system, use completeness to reduce to the semantics, and start the proof search with the labeled proof system of Sara Negri. And either you give a proof, you construct the full proof and you end with a proof of your proposition, or if it fails, you obtain a counter model. The counter model is not certified in some sense, but it's easy to verify the counter model that you obtain. So to give an example, say you want to prove the second incompleteness theorem in GL, you can state this is the instruction in a HOL that state the theorem. You use a tactic which is called GL tac for proving the theorem, and you obtain the theorem because you have a proof of that. Otherwise, you start with another formula which is not a theorem of GL, which has a simple counter model in this case. So you state your, you start your proof, you use your tactic, you obtain an error, which says that you cannot obtain the proof, but you have a counter model. You can get the generated counter model, which has this form in the output of the whole light, and which is represented by, which represent this diagram on a counter model where you have 3 words which are related in this way. Okay, so to recap, we implemented a deep embedding of the GL probability logic, and we proved the soundness and completeness of the system. We provided a decision procedure, and what we would like to do is generalize this approach to other modal logics and prove the arithmetic completeness of GL. Okay. Thank you.
Thank you.